How's it going, everybody out there? In this video, I'm going to be talking about section 3.2, logarithmic functions. Logarithmic functions are the most useful to us for like sound technicians and people like that. They help calculate the cents or the hertz between each note. Pretty much, if you are going into sound, if you are going into music, you may want to know something a little bit about logarithms so that you can do certain things and create cool new sounds, because we all know that it's not going to be like just Led Zeppelin music forever. You're going to have to create music that just goes beep bop boop beep bop boop, right? And that's I don't know where music's going. Who knows? But anyways, there's two different ways of writing logarithms, so let's explore that really quick. So here are the two different ways you can write it. We have explored exponential form. That's what we did in well, that works. Section 3.1, right, where we have a base. Well, in logarithmic form, that same number is also the base, so I can rewrite these as either one. They're interchangeable with each other. That is what's cool about exponential and logarithmic. They're actually inverse functions of each other as well, but we'll get to that later. We have an exponent. The exponent is what it is equal to. Exponent. Right, and then x is just some random number that you are taking the log of. You need to be able to convert between each form very easily. So let's look at a few examples and just convert them. All right, in this example, it gives you an exponential function. I can tell that because it has an exponent. Yay. Exponential function. It looks like it's an exponential form. B to the y equals x or something like that. Yay. Yay. We acknowledge that it's exponential form. And it says rewrite it to the logarithm. So I'm just going to go from my exponential form to my logarithmic form. So banana phone. I have my base, I have my exponent, and I have a number at Ben. So I can say log of base 3 with the number on the inside equals the exponent, which is 4. That is logarithmic form. Okay, so it would be the same thing otherwise. You would be given rewrite as in exponential, and you would be given this, so you could say 3 to the 4 equals x. 3 to the 4, 3 to the 4th power. Let's look at one of those anyways. All right, in this example, I'm given a logarithmic form, asking me to rewrite it as an exponential. So the way I see this is I say 2 to the 8th power, so 2 to the 8th equals x, and that is it. The way I kind of logic through that in my head, or at least tell myself to just kind of remember, that 2 is the lowest. I know that these can't go together, so I raise it to the other number that I could possibly have, which is 8. So 2 to the 8th power, 8, equals the number inside equals x. Like I said, you need to be able to move these around very easily, go between each form very easily. Now this looks what? Let's look at some raw words. Let's look at some log truths, yo. There we go. Okay, so these are all of the things that you need to know about logs. Definitely know these things. If you don't, it's not a huge deal, but it's a pretty big deal. So with this, I probably should have written this first, but really, you need to know these. If you have a log and you do not see a base, it is understood to be 10. If you have a natural log, ln means natural log, write it as ln. French guy came up with it, he called it logarithmic natural, or something like that, I don't know. But that's why, because in French the words are actually reversed. So this is called a natural log in English. It is ln because a French mathematician came up with it. If you do not see a base, it is understood to be e. So with these first ones, I'm going to explore this one right here. If you have the log of 1, it equals 0. Likewise, if you have the natural log of 1, it also equals 0. So let's see why that is true. Let's say we do not know what it is equal to. Log base 1, or log base 10 of 1 is understood to be 10 if it's not a log, right? Or if there's no base there, understood 10. I don't know what it equals, but I can rewrite this as exponential form, say 10 to the what power equals 1. Well, the only thing that I can raise to the power, the only power that I have that creates a value of 1, other than with the number 1, is if x were equal to 0. Anything to the 0 power is equal to 1. Cool. Okay, that is that one explored. If I have one of these down here, if your base is the same as the number, it is the power that it is equal to. So again, let's say that I don't know what it is. Log base 10. Log base 10, 10, y equals, I have no idea, but let's say x. Okay, so if I rewrite this as exponential, I can say 10 to the x power, 10 to the x power equals 10 to the y, because that is my number on the inside. Well, then I know that x has to equal y, so then y should be the thing over here, which is exactly what we are saying in our truth, yo. Homie G dog, logarithmic truth, man. Word on the street, brother. Something like that. I don't know. I'm sorry. I'm strange. You know that by now. You've watched enough of these things. Okay. And then our last one that we are going to explore, 10 to the log x equals x. I'm going to actually explore this one just so we do one with a natural log. E to the ln 10 is equal to 10. Pretty much, base here is the same as the base here. It is just the number inside. So let's check it out. Check it out. What's it all about? Work it out. We're going to turn this. I just don't know what I'm saying really anymore. So this is written in exponential form because it is being raised to the exponent. So if I rewrite this in logarithmic form, I have the base, so ln base e, x equals ln 10. Well, I know that the understood base there is to be e, so x must be 10. Since they both have the same base, the numbers inside must also be equal. So that is why that is equal to 10. Right, and it would also go if like we had e to the ln 4. This should just be 4. Or e to the ln 207. This should just be 207 because the bases are the same. They don't really go away, but I just know they're equal to the number on the inside. Cool. Let's do some more problems. Yay. All right, so this one here is one you would see without the calculator. Evaluating this logarithmic function. Well, if that's a base of 9, and I know from my truths that if that were a base of 9, it would just be equal to the exponent. Well, 81 is 9 squared, so if I rewrite this as log base 9 of 9 squared, well, hey, oh, it's equal to the exponent. Cool. Pause it. Pause it. You guys are going to love this one. Well, base is the same as the base, so 1. Yay. Again, make sure you know your truths. If you don't, you're going to have some issues. Pause it. Okay, and one like this you would actually have your calculator for. So our handy dandy calculator, if we just punch in log of 0.081, hey-oh, negative 1.09. Cool. Negative 1.09. That's not a comma, that's a period. Yay. And likewise, one like this you would also have the calculator for. So your base is e. There's no way that we can rewrite 32 in the base of an e. So I can say that my calculator will tell me the answer. Punch it in. Yay. 3.465, 3.466, 3.466. I need a yellow pink pen. 3.466. Yay. Yay. So pretty. So pretty, I'll draw a bow. Oh, yay. Do not forget that your understood base of the natural log is e, so e to the 4. Yay, I know my properties. All right, and one like this, you're going to have to bring back a little bit of algebra skills to remember that if you have something like this, you can rewrite this as e to the negative 3 if you move it up top. So you have natural log of e to the negative 3. Your bases are the same, so there's just negative 3. Yay. And notice how fast those go. As long as you guys know your properties, it will go just as fast. And you'll be able to take your test fast and your quiz fast, and you'll know everything fast. So make sure you study. Make some note cards. Lots and lots of note cards. Well, 1, 2, 3, 4, 5, 6, 7, 8, maybe 8 note cards. Yeah, you don't need that many. Study. You got it. It's not hard. Just learn it. All right. Now we're going to look at a little bit at the graphs of logs. If we have our log function, where we have a base of b, if the base is greater than 1, we will have a function that is increasing the entire time. If we have a base that is less than 1, we will have a function that is decreasing the entire time. So this is kind of just like exponentials, where our base was bigger than 1, it was increasing, base less than 1, it was decreasing. You just kind of have to remember what the graph looks like. So to kind of help me out, I imagine that this is like a man. I mean, there's his body and his legs, and he has to jump over a log head first, right? So he's jumping over a log. Yay! Okay, so let's look at a few characteristics of different types of graphs. And one other thing that I forget to tell people about all the time is that don't forget that you have a vertical asymptote at x equals 0 on both of these. Vertical asymptote, x equals 0. both of them, every time you have a log function. All right, we're going to look at this example and determine a lot of things, so I'm going to go ahead and take a second, and you take a second to go ahead down and write down the problem. I don't know what I just said, but I'm going to write down all the other things too. So here we go. All right, so here's everything that I'm going to state about this function, except for what I'm writing right now, which is in behavior. I apologize. Hang on a sec. Okay, there we go. So in this one, I noticed that my base is 4. 4 is greater than 1, so I know I will have a log function that looks something like this, where it is increasing the entire time. So I can go ahead and say that increasing is going from negative, not from negative infinity. It is going from 0 to infinity because it is going to keep getting closer to this, but remember this is our vertical asymptote, so I have an asymptote at x equals 0. My end behavior as x goes to negative infinity, so it is going to the left forever and ever and ever. It is going to get closer and closer to my y-axis, but it is going to go to negative infinity because it is going down forever. Oop, there it is, negative infinity. And as x is going to infinity, it is going to infinity. X is going up forever. Okay, for your domain, I cannot have anything to the left of this vertical asymptote, so I have everything from 0 to infinity. My range is negative infinity to infinity. My x-intercept, if I substitute 0, I have 4 to the 0, if I rewrite that function, equals x, so that would be 1. And the y-intercept, if I substitute a 0 for x, that is not possible because that is only asymptote, so I will have no y-intercepts. Okay, we're going to move these things around some too, but we will talk about that a little bit more, especially when we get into 3.4 when you can actually do those things. So make sure you guys practice this, make sure you know your properties, and as long as you do those few things, you should be good to go. Love you. See you in your class. Bye!